Imagine being trapped in your own mind, able to think clearly, but unable to say a single word. For many living with severe paralysis, this is a daily reality. But groundbreaking new research might be about to change everything. Intrigued? You should be, because these advances could fundamentally reshape how humans communicate. But here's where things get controversial. At Stanford Medicine, an innovative team led by Assistant Professor of Neurosurgery Frank Willett, PhD, has created a remarkable brain-computer interface, BCI, that reads what people with speech impairments are thinking directly from the brain and translates those thoughts into digital words. This potential breakthrough offers a ray of hope for restoring swift and natural communication to those who have lost their speaking ability due to paralysis. So, how does this futuristic technology actually work? It begins with tiny microelectrode arrays. Imagine something smaller than a pea being surgically placed onto the surface of a patient's brain. These arrays are capable of capturing unique patterns of neural activity generated when a person tries or even just imagines talking. The captured signals are transmitted to a computer, where specialized algorithms decode them into meaningful actions, be it moving a computer cursor or producing speech. Here's where it gets even more fascinating. The research team, including postdoctoral fellow Aaron Coons and graduate student Benjamin Abramovich Krasa, has harnessed the power of machine learning to link specific brain activity patterns with individual speech phonemes, the smallest building blocks of spoken language. By assembling these phonemes, the system can construct entire sentences, opening up vast possibilities for people unable to communicate in conventional ways. And this is the part most people miss. Previous work by Willett and his collaborators already demonstrated these BCIs could successfully capture the brain signals produced when a paralyzed person attempted to speak or write, even if the signals never resulted in actual movement. Now, they've gone a step further by exploring the concept of inner speech, the silent voice in your head when you imagine speaking to yourself, sometimes called your inner monologue. But why is decoding inner speech such a game changer compared to just capturing attempted speech? Simply put, making attempts to speak after paralysis can be exhausting, lead to sound distortions, and strain breath control if any limited movement remains. Inner speech, by contrast, is completely silent and effortless. If a BCI could accurately interpret these purely imagined utterances, users might finally regain the ability to speak at normal speed and with minimal strain. To test this possibility, the Stanford researchers worked with 4 individuals suffering from profound speech and movement impairments. After implanting the microelectrode arrays, they discovered something remarkable. The brain's motor areas light up with distinct, robust patterns during inner speech, much like during attempted speech, just at a smaller scale. Even at this early stage, their system could decode these inner speech signals well enough to prove the concept, raising real hopes for future breakthroughs. Yet, as with any breakthrough, new dilemmas emerge. Here's the controversial twist. If technology can accurately decode silent thoughts, where does privacy end and mind reading begin? What if the BCI picks up on an idea the person never intended to share? Although current technology isn't precise enough to transcribe inner monologue word for word, the potential exists, and researchers are actively working on solutions. For now, BCIs are strictly regulated and far from common use, but the privacy implications are already a hot topic. Addressing these concerns, the team developed a twofold solution. Current BCIs were programmed to distinguish between attempted and inner speech, effectively filtering out thoughts that shouldn't be spoken. For future systems designed to work with inner speech, they unveiled a clever password-based protocol. The device will only decode inner speech if the user first imagines a special, unlikely to be accidentally thought phrase, like as above, so below. Both approaches proved extremely effective in guarding against unintended thought leaks. Looking ahead, where does this research go next? Advancements in hardware promise more compact, wireless implants capable of recording more neurons, paving the way for faster, more reliable BCIs. Numerous companies are racing to develop these fully implantable systems. Meanwhile, the quest continues to identify brain regions outside the motor cortex, such as those involved in language processing or hearing, that might improve decoding accuracy for imagined speech. But here's a question for you. Would you ever trust a machine to read your silent thoughts? Could society draw the line between assisting those in need and protecting mental privacy? Or is this concern merely a fear of the unknown? Agree, disagree, or have your own take? Let's continue the conversation below. Your opinion could shape the direction this technology takes.